Hello students, welcome to this lecture on adaptive filters. Let us review that the filter coefficients of an adaptive filter are updated based on the error En between the filter output and the desired signal Dn. The cost function E of E square n for an FIR winner filter is quadratic in Hn and a unique global minimum exists. The optimal set of filter parameters can be found by the SDA, steepest descent algorithm iteration, which is given by h of n plus 1 is equal to Hn plus mu by 2 times negative of the gradient of E of E square, and this is the steepest descent iteration. So, iteration in the direction of negative of gradient. In terms of autocorrelation matrix Ry and the cross correlation vector small r dy, this updating can be written as h of n plus 1 is equal to Hn plus mu times r dy minus Ry into Hn matrix. This SDA iteration converges if the step size parameter mu satisfy this relationship. 0 is less than mu less than 2 by lambda max, where lambda max is the maximum eigenvalue of the Ry matrix. A simpler condition for the convergence is given by mu lies between 0 and 2 by m into Ry 0, where m is the length of the filter. The SDA can be modified to update the filter coefficients adaptively to derive a very powerful adaptive filter algorithm. This algorithm is called the least mean square LMS algorithm and is due to Withdrawn of 1960. This lecture will discuss the LMS algorithm. We will see how the cost function is modified for LMS algorithm. Consider the basic setup as shown in this figure. Here Yn is the input to the adaptive filter and its output is d hat n, which is compared with this desired signal Dn, and the error is used to update the filter coefficient according to the adaptive algorithm, and those filter coefficients are used in the adaptive filter. We will consider an m length FIR filter Hn, that is filter coefficients are given by H0 n, H1 n up to Hm minus 1 n. And the signal vector Yn comprising of Yn, Yn minus 1 up to Yn minus m plus 1. The winner filter considers the cost function expected value of E square n, that is the mean square error, that is equal to E of Dn minus, this is the filtered output H transpose n into Yn whole square, and this we can write as E of Dn minus summation H I n into Yn minus I going from 0 to m minus 1 whole square. In the LMS algorithm, E of E square n is replaced by E square n to achieve a computationally simple algorithm. So, modification is very simple, just E of E square n, you are replacing it by E square of n. Therefore, the cost function is given by E square n is equal to Dn minus H transpose n into Yn whole square, that is equal to Dn minus summation Hin into Yn minus I going from 0 to m minus 1 whole square. So, this is the cost function for the LMS algorithm. the cost function is now dependent on the data rather than the second order statistics, because we know that in the case of Wiener-Hoff solution, the solution is in terms of the second order statistics, that is cross correlation matrix and autocorrelation vector. The optimization problem is reformulated as minimize square n with respect to the filter coefficient vector Hn. This is the LMS optimization problem. The optimization is no longer deterministic. It is a stochastic optimization problem. Why? Because square n, it is dependent on the data which are random. This SDA method will now be called stochastic gradient method. Steepest descent algorithm will be used here, but it will be called the stochastic gradient. It is the gradient of a random quantity. We will discuss the LMS algorithm. Consider the steepest descent relation, that is iteration. H of n plus 1 is equal to Hn minus mu by 2 into gradient of E of square, and here this 2 is used because we will get a 2 terms because of this gradient, both of them will cancel. Where that gradient of E of square n is given by this vector, first component will be del H naught of E of square n, like that. Last component will be del H m minus 1 of E of square n. And mu is the step size parameter. Therefore, for the convergence of the iterations, we have to choose this mu parameter properly. Now, the gradient of square n is given by gradient of square n is equal to 2 times En into this vector del En del H naught up to del En del H m minus 1. Because it is a function of a function, so first we have to consider a derivative of square n, that is twice En, then derivative of En with respect to each of the parameter. Gradient of square n is called stochastic gradient because the error is a random quantity, because En is derived from the random data, therefore it is a stochastic quantity, and corresponding gradient of square n is stochastic gradient. Now, consider the error En, that is equal to Dn minus the filtered output. Filtered output is summation Hin into yn minus I going from 0 to m minus 1. This is the error signal. Now, taking the partial derivative, del En del Hj is equal to, this negative sign is there, we are taking the partial derivative with respect to Hj, so only yn minus j will be there. So, therefore, del En del Hj is equal to minus y of n minus j, j going from 0 to m minus 1. So, that way partial derivative of En with respect to Hj is given by negative of y n minus j. The partial derivative factor is now given by negative of this factor yn minus 1 up to yn minus m plus 1, that is equal to minus yn vector. Therefore, gradient of square n will be minus 2 times En into yn vector from this relationship. Gradient of square n is equal to 2 times En into this partial derivative vector. So, from that we get that gradient of E square n is equal to minus 2 times E n into y n. This steepest descent update now becomes h sub n plus 1 is equal to h n plus mu times E n into y n. Now, updating is in the direction of y n instead of in the direction of the gradient of the mean square error. So, the updating is in the direction of data vector. This modification is due to withdraw and hop as we have told earlier, and the corresponding adaptive filter is known as the LMS filter. We can give the steps of LMS filter. Given the input signal yn, the desired signal dn, the filter length m, and the step size parameter mu. These are the input to the algorithm. Initialization hi0 is equal to 0 for I is equal to 0 up to m minus 1. All the filter coefficients are initialized to 0. Now, this is the updating for n greater than 0. Filter output is d hat n, that is equal to h transpose n into yn. So, yn is passed through the adaptive filter, that output is d hat n. Estimation error En is equal to dn minus d hat n. Now, the filter coefficient will be adapted as h sub n plus 1 is equal to h n plus mu En into yn vector. Now, we describe the LMS algorithm based adaptive filter setup. Here yn is the input. This is passed through the FIR winner filter of step length m minus 1. Then we will get the estimate of the desired signal. And this is the desired signal which we have to decide. So, this is positive, this one is negative. So, that difference is the error signal. This error signal is passed to the LMS algorithm, and there the filter coefficient will be updated according to the error, and the filter coefficient will be passed over to the FIR adaptive filter. So, that way this LMS algorithm has two input. One is the data itself, because data vector is needed there, and this side is the error signal. Let us consider one example. The input to a communication channel is a test sequence given by xn is equal to 0.8 xn minus 1 plus wn, where wn is a zero mean unity variance white noise. This channel transfer function is given by hz is equal to z inverse minus 0.5 z to the power minus 2. So, this is an FIR filter, and this channel is affected by white Gaussian noise of variance 1. Find the FIR winner filter of length 2 for channel equalization. Choose a value of mu and write down the LMS filter update equations. First, we will show the filter setup. The filter setup is like this. The test sequence xn is passed through a delay to the receiver. So, that way dn is the test sequence, but it is delayed by some amount. Now, the test sequence is passed through the channel whose transfer function we know, and then there is a addition of noise. So, this Vn noise is added here, and the output is passed to the adaptive filter. The adaptive filter will estimate d hat n. So, d hat n will be estimated, and the error will pass over to the LMS algorithm. So, this is the channel equalization problem. Here this is the test sequence, this is passed through the receiver as it is, but there is a communication delay that to the power minus L, that is L unit of time delay. Then this test signal is passed through this channel. There is addition of Gaussian noise and the output is Yn, and this is filtered by the adaptive filter of length 2. The estimated signal is d hat n, and the corresponding error is sent to the LMS algorithm for updating the filter coefficients. Let us solve the problem. Transmitted signal is an AR1 signal. What is this? Xn is equal to 0.8 xn minus 1 plus Wn. Recall the AR model in our earlier lecture. We know that autocorrelation function, which was derived from the Yule-Walker equation, is given by Rx of m is equal to sigma w square divided by 1 minus 0.8 square into 0.8 to the power m, and here sigma w square is equal to 1. So, if we carry out the calculation, we will get Rx of 0 is equal to 2.78, Rx of 1 is equal to 2.22, Rx of 2 is equal to 1.78, and Rx of 3 is equal to 1.42, like that. Now, channel transfer function is given by Hz is equal to z to the power minus 1 minus 0.5 z to the power minus 2. This is an FIR filter. Therefore, we can write output of this filter, that is Xn is this is passed through Hz. So, output will be Yn is equal to x of n minus 1 minus 0.5 x n minus 2 plus Vn. So, this is the output of the FIR filter. Therefore, Rym will be equal to E of Yn into Yn minus m, and this will be equal to E of x of n minus 1 minus 0.5 x n minus 2 plus Vn into x of n minus 1 minus m minus 0.5 times x of n minus 2 minus m plus V of n minus m. So, we have to find out the expectation of this quantity. And if we carry out the multiplication and then take the expectation, we will get first term will be 1.25 into Rx of m, because it will be E of x of n minus 1 into x of n minus 1 minus m. So, that way we will get Rx of m, and this also 0.5 x n minus 2 into 0.5 x n minus 2 minus m. This will also give Rx of m. So, this will be 0.5 into 0.5, 0.25 Rx of m. So, that way we will get here 1.25 Rx of m. Similarly, there will be the cross terms. So, because of that we will get minus 0.5 Rx of m plus 1 and minus 0.5 Rx of m minus 1. And this noise is of variance 1, and they will be uncorrelated with the signal and uncorrelated with the sample of the noise also, but only when m is equal to 0 there will be the correlation, that is the variance. So, that way this term will be delta m, and that variance is equal to 1. Therefore, Rym will be equal to 1.25 Rx of m minus 0.5 Rx of m plus 1 minus 0.5 Rx of m minus 1 plus del m, and we know the values of Rx of m. Similarly, we can find out the Rxym, that is equal to E of xn into x of n minus 1 minus m minus 0.5 x n minus 2 minus m plus V of n minus m. This is the Yn minus m, this is xn. So, that way Rxym, we write it as this is equal to E of xn into y n minus m. So, that way if we substitute y n minus m by this expression, we will get this result. So, that way r x y m is equal to r x of m plus 1 minus 0.5 into r x of m plus 2. It means that r x y of 0 is equal to 1.33, r x y of 1 is equal to 1.07. We have here r y of 0 is equal to 2.255, r y of 1 is equal to 0.5325. So, we have the autocorrelation and cross correlation values. So, we can solve the Wiener-Hopf equation. Therefore, the Wiener-Hopf equations are given by this autocorrelation matrix comprising of ry0, ry1, ry1, ry0 multiplied by the coefficient vector h0, h1 is equal to the cross correlation vector, that is rxy0, rxy1. And if we substitute the values, we will get this matrix multiplied by h0, h1 is equal to this cross correlation vector comprising of 1.33, 1.07. Solving, we get h0 is equal to 0.51 and h1 is equal to 0.35. Now, let us see how to get the LMS solution. So, we have to get dn in this diagram. So, that way dn is a delayed version of xn, that is also input to the algorithm, and ry is given by this. In this case, we can determine what should be the value of mu, because ry is given. Therefore, one convergence relationship is that mu which is positive should be less than 2 by trace of ry, and trace of ry is equal to 2.255 plus 2.255. So, that way it will be 4.51, and therefore, mu is equal to 1/3 is a choice for the SDF, because here we have not yet discussed how to choose mu for the LMS algorithm. Now, the LMS iteration will start. Length to FIR filter Hn, that is H0n and H1n transpose. These are the two filter coefficients. And the data vector yn is given by this two component vector comprising of yn and yn minus 1. Then the output of the adaptive filter d hat n is given by H transpose n into yn, that we can compute, the algorithm will compute, and En is given by dn minus d hat n. Dn already we know, d hat n we have computed here, therefore, we can compute En. The LMS recursion is now given by h of n plus 1 is equal to Hn, which we have defined here, plus mu times En into Yn. In this way, we can update the filter coefficient. Let us summarize the lecture. The LMS algorithm reformulates the Wiener filtering problem as minimize E square n. Instead of E of E square n, it is minimize E square n with respect to the filter coefficient vector Hn. So, this is a stochastic optimization problem. Gradient of E square n is called the stochastic gradient because the error En is a random quantity. The filter weights are updated according to the relation h of n plus 1 is equal to Hn plus mu times En into Yn, where Yn is the data vector and En is the filtering error. We introduced the LMS algorithm. It is a very simple algorithm, but the convergence analysis of this algorithm is quite difficult. We will discuss this in the next lecture. Thank you.